Chapter 1 Units and Measurement. Physics. Physics comes from the Greek word nature. Physics is concerned with explaining how energy, matter, space, and time interact in order to identify the basic mechanisms that underlie every phenomenon. This concern for describing the fundamental natural events defines the scope of physics. Physics aims to understand the most basic level of the world around us. It emphasizes the use of a small number of quantitative laws to do this, which can be useful to other fields, pushing the performance boundaries of existing technologies. Knowledge of physics is useful in everyday situations. For example, how microwave ovens work, or operation a car's ignition system. Physics has many applications in the biological sciences as well as chemistry. Order of magnitude. The order of magnitude of a number is the power of 10 that most closely approximates it. The order of magnitude refers to the scale of a value. Each power of 10 represents a different order of magnitude. For example, 10 to the power of 1, 10 to the power of 2, or 10 to the power of 3. The order of magnitude of a number is designed to be a ballpark estimate for the scale or size of its value. It is simply a way of rounding numbers consistently to the nearest power of 10. Here's the example of the orders of magnitude of distance in meters. We're going to read some definitions that are useful in physics. Model. A model is a representation of something that is often too difficult to display directly. Physicists use models for a variety of purposes. For example, models can help physicists analyze a scenario and perform a calculation, or models can be used to represent a situation in the form of a computer simulation. Theory. A theory is a testable explanation for patterns in nature supported by scientific evidence and verified multiple times by various groups of researchers. Some theories include models to help visualize phenomena, whereas others do not. Newton's theory of gravity, for example, does not require a model or mental image because we can observe objects directly with our own senses. A law uses language to describe a generalized pattern in nature supported by scientific evidence and repeated experiments. Physical quantity. We define it either by specifying how it is measured or by stating how it is calculated from other measurements. For example, we might define distance and time by specifying methods for measuring them, such as using a meter stick and a stopwatch. Then we could define average speed by stating that is calculated as the total distance traveled divided by time of travel. Units. Measurements of physical quantities are expressed in terms of units. Without a standardized unit, it would be extremely difficult for scientists to express and compare measured values in a meaningful way. SI units. In any system of units, the units for some physical quantities must be defined through a measurement process. These are called the base quantities for that system, and their units are the system's base units. All other physical quantities can then be expressed as algebraic combinations of the base quantities. Each of these physical quantities is then known as a derived quantity, and each unit is called a derived unit. Measurement. Measuring is essential in science. We can put a quantity to an object or an action. How to take measurements. For measuring an object, we need first choose a tool like a ruler. With the tool, we write a number that we measured. Writing the units down is the most important part of our measurement system. Measurement of any physical quantity without a unit is meaningless. The number of digits we report matters, and it is based on the tool we use. Precision and accuracy in measurements. Accurate. It matches the correct value or standard. This means we use the tool correctly. Accuracy is how close a measurement is to the accepted reference value for that measurement. Precise. It's consistent. It means we get the same number every time, and it's going to have the right number of digits for the tool. The precision of measurements refers to how close the agreement is between repeated independent measurements, which are repeated under the same conditions. Significant digits or figures. It means how many digits we write down. When we are counting objects, we use exact numbers. We use precise figures for counting. Using the method of significant figures, the rule is that the last digit written down in a measurement is the first digit with some uncertainty. To determine the number of significant digits in a value, start with the first measure value at the left and count the number of digits through the last digit written on the right. For example, the measured value 58.6 cm has 3 digits or 3 significant figures. Significant figures indicate the precision of the measuring tool used to measure the value. Solving problems in physics. Problem-solving skills are essential to success in a quantitative course in physics. Strategy. Strategy is the beginning stage of solving a problem. 1. Examine the situation to determine which physical principles are involved. 2. Make a list of what is given or can be inferred from the problem as a state. Identify the knowns. 3. Identify exactly what needs to be determined in the problem. Identify the unknowns. 4. Determine which physical principles can help you solve the problem. Solution. The solution stage is when you do the math. Substitute the knowns along with their units into the appropriate equation and obtain numerical solutions complete with units. Significance. After having done the math in the solution stage of problem solving, it is tempting to think you are done, but always remember that physics is not math. Rather, in doing physics, we use mathematics as a tool to help us understand nature. So after you obtain a numerical answer, you should always assess its significance. First, check your units. Second, check the answer to see whether it is reasonable. And the last, check to see whether the answer tells you something interesting.